Chapter 14. Chapter 14. Special Purpose Integrated Circuits, Revision and Questions. The instrumentation amplifier, these are basic formulas what you need to know of an instrumentation amplifier, of an insulation amplifier, for a transconductance amplifier or the OTA circuits, a specific OTA LM13700, the lock and anti-lock amplifiers, converters, and other op-amp circuits. Now let's start with typical general knowledge. A typical instrumentation amplifier has a high common mode rejection ratio, a unity gain, a low input impedance, all of above. The correct answer is a high common mode rejection ratio, because an instrumentation amplifier indicated as IA amplifiers the voltage difference between its terminals. It is optimized for small differential signals that may be riding on large common mode voltages. When the instrumentation amplifier uses guarding, the shield is driven by a low impedance differential source, low impedance common mode source, a high impedance differential source, a high impedance common mode source. The correct answer is B, a low impedance common mode source, because we know by now that the voltage follower is a low impedance source that drives the common mode signal onto the shield to eliminate the voltage differences between the signal lines and the shield. Number 3, you can achieve higher bandwidth for instrumentation amplifier if you use guarding, use a larger gain setting resistor, capacitively couple the input signal, none of above. The correct answer, none of above, because we know instrumentation amplifier is normally used to measure small differential signal voltages that are superimposed on a common mode voltage, often much larger than the signal voltage. An amplification where an insulation amplifier is particularly useful is when the input signal has a very large dynamic range. Control of a frequency response is necessary. Voltages could present a hazard, all of the above. The correct answer is C. Voltages could present a hazard. Insulation amplifiers are common in patient monitoring applications to avoid potential shock from a monitoring equipment. For an operational transconducer amplifier or OTA, the gain is determined by a ratio of 2 resistors, bias current, a single gain setting resistor, the amplitude of the input signal. The correct answer is a bias current, because for operational transconductance amplifier is primarily a voltage to current amplifier in which the output current equals to the gain times the input voltages. Transconductance is the ratio of output current to input voltage, input current to output voltage, output resistance to input resistance, output voltage to input current. The correct answer is output current to input voltage, because as in the case of FETs, the conductance is output current divided by the input voltage. Thus, GM is equal to I out divided by V in. A circuit that is useful for signal compressing is instrumentation amplifier, OTA, logarithmic amplifier, anti-lock amplifier. The correct answer is the logarithmic amplifier, because we know lock and anti-lock amplifiers are used in applications that requires compression of analog input data, linearization of transducers that have exponential outputs, and analog multiplication and division. The circuit shown here is a peak detector, current to voltage converter, a voltage to current converter, insulator amplifier. Correct answer, a voltage to current converter, because a basic to current converter is shown in figure 14.38 in your textbook. This circuit is used in applications where it's necessary to have an output load current that is controlled by the input voltage. The next circuit that is indicated here is a current to voltage converter, a constant current source, a logarithmic amplifier, an anti-logarithmic amplifier. This is an anti-log amp. The anti-log amplifier is formed by connecting a transistor or a diode as the input element, as shown in the figure here. The circuit shown here is a current to voltage converter, voltage to current converter, constant current source, a peak detector. This is a peak detector. Of course, an interesting application of op-amp is in a peak detector circuit such as the one shown in this figure here. In this case, the op-amp is used as a comparator. This circuit is used to detect the peak of the input voltages and store the peak voltage on a capacitor. The next answer is true or false. I make the statement that a basic instrumentation amplifier has 3 op-amps, and that is true. Next one of the key characteristics of instrumentation amplifier is its low input impedance. Correct answer there, it is false because you got a high input impedance. The voltage gain of instrumentation amplifier is set with an external resistor, and that is true. A basic insulation amplifier has 2 electrically insulated sections. Answer is true. Most modern insulation amplifiers use transformer coupling for insulation. False. OTA stands for operational transistor amplifiers. That is false. Number 7. A lock amplifier has a JFET in the feedback loop. Disagree, that is false. An anti-lock amplifier has bipolar junction transistors in series with the input, and that is true. The main purpose of an instrumentation amplifier is to amplify common mode voltages. Answer is false. The OTA is a voltage to current amplifier, and this statement is true. Linear signal compression scales down the signal levels by the same amount. This statement is also true. The next one, the OTA has a high input impedance and a low common mode rejection ratio, or has a low input impedance and a high common mode rejection ratio, or a high input impedance and a high common mode rejection ratio. The correct answer is C, a high input impedance and a high common mode rejection ratio. Now let's refer to the figures above. There's A, B, C, and D. In this particular case, which of these circuits is known as the anti-lock amplifier? And we all know the anti-lock amplifier is going to be number D. Why? Because an anti-lock amplifier is formed by connecting a transistor or a diode as the input element. Which of these circuits is known as a constant current source? That is B. The reason for that is a constant current source delivers a load current that remains constant when the load resistance changes. Vin provides a constant current of In through the input resistor Ri. Since the inverting that negative input of op-amp is at virtual ground or 0 volts, the value is determined by Vin and Ri. Which of these circuits is known as an insulation amplifier? The correct answer is C. An insulation amplifier is a device that consists of 2 electrically insulated stages. The input stage and the output stage are separately from each other by an insulation barrier, so that the signal must be processed in order to couple across the insulation barrier. Here in this particular case, you can see the insulation barrier is basically a capacitor. Which of these circuits is known as the instrumentation amplifier? The correct answer is A. The instrumentation amplifier is a differential voltage gain device that amplifies the difference between the voltage existing at 2 input terminals. The main purpose of instrumentation amplifier is to amplify small signals that may be riding on large common mode voltages. Op-amps A1 and A2 are non-inverting configurations that provide high input impedances and voltage gain. Op-amp A3 is used as a utility gain differential amplifier with high precision resistors that are equal in value. In other words, R3 is equal to R4 is equal to R5 and is equal to R6. If we refer to the figures above, if R1 is equal to R2, to figure A above, sorry, if R1 is equal to R2, and that's equal to 30K, and the closed loop gain is 450, the value of external gain setting resistor RG is equal to, we make use of a formula, RG is equal to 2 times R1 divided by A open loop, closed loop gain minus 1. If you substitute that values, you will get hold of a value RG is equal to 133.63. So in other words, the correct answer for this problem is B. Now we refer to figure A. If R1 is R2 is equal to 28 ohm, RG is 100 ohm, and AC1 would be, what would AC1 would be? ACL is 1 plus 2R divided by RG. Substitute the values and you get hold of a value of 561. So in other words, the correct answer is C. Now we refer to figure B here. If VIN is equal to 5 volts and IN is equal to 22K, the current through the load resistor would be, we make use of a formula, IN is VIN over RIN. Substitute that values and you find IN is 5 divided by 22K, and that is equal to 227.72 microohm. We know that IL is equal to IN in this particular configuration. So therefore, the correct answer should be 227.27 microfarad as indicated in D. Now we refer to figure D, that is this particular one here. If V1 is 200 millivolts, RF 52 kilo ohm, IEBO is 50 nanoamp, then V out would be, we make use of, to get the algorithm, you must take the exponential of a logarithmic anti-logarithm of x is equal to e to the power ln x. Since KT divided by Q is approximately 25 millivolts, V out is equal to negative RF multiplied by E, IEBO, anti-log V in divided by 25 millivolts. Substitute that values and you get hold of a value. V out is negative 2.6. Press in your calculator that calculation there, and you get V out is minus 2.6 exponent of negative 3 multiplied by 2980.958. And that gives you a value of minus 7.75. So the correct answer is C. Refer to the figure above. Which of these circuits is known as a constant current source? Constant current source is B, because a basic circuit in which stable voltage sources V in provide a constant current I in through the input resistor R in. Since the inverting input of an op-amp is a virtual ground 0 volts, the value of is determined by V in and Ri, as I in is equal to V in divided by Ri. Which of these circuits known as a current to voltage converter? Correct answer is A. Current to voltage converter converts a variable input current to proportional output voltage. Since practically all of I in is through the feedback path, the voltage drop across RF is equal to I in multiplied by RF. Because the left side of RF is at virtual ground, the output voltage is equal to the voltage across RF, which is proportional to I in. Which of these circuits contains operational transconductance amplifier? That is D. Transconductance of an electronic device is the ratio of the output current to the input voltage. if you look here to figure B, if RL is 20K, RI is 1.2K, V in is 2.5 volts, the load current IL would be, make use of a formula, I in is equal to V in divided by R in. Do that calculation there, and I find I in is 2.083 milliamps, and we know that IL in this particular case is equal to I in. So the correct answer, 2.083 milliamps, is equal to B. Refer to figure above. If your GM is 25 millisiemens, RL is 25 kilo ohm, the voltage gain would be, make use of a formula, voltage gain is GM multiplied by RL. So AV is 25 millisiemens multiplied by 25K. That gives you 625. So the correct answer in this case is A. Choose the correct answer. The input signal for instrumentation amplifier usually comes from an inverting amplifier supply, a filter DC power, a differential amplifier, a Wheatstone bridge. And the correct answer is a Wheatstone bridge. Instrumentation amplifiers are well suited for environments with no signal and no noise, high signal levels that needs to be attenuated, no power supply voltages, small signal superimposed on large common mode voltages. Correct answer is D, small signals superimposed in large common mode voltages. An instrumentation amplifier has a high output impedance, high power gain, high common mode rejection ratio, or high supply voltage. The high common mode rejection ratio, number C. An input transducer converts voltage to current, current to voltage, electrical quantity to a non-electrical quantity, a non-electrical quantity to electrical quantity. The correct answer is a non-electrical quantity to an electrical quantity. In some respects, an isolation amplifier is nothing more than an elaborated op-amp, instrumentation amplifier, rectifier and filter, both A and B. Correct answer is both A and B. It's an op-amp as well as instrumentation amplifier. The primary function of oscillator in an isolation amplifier is to convert DC to high frequency AC, convert DC to a low frequency AC, rectify high frequency AC to DC, produce dual polarities, DC voltages for input to the demodulator. Correct answer, convert a DC to a high frequency AC. The voltage gain of an O to A can be calculated using the formula. AV is RF divided by RI. AV is GM multiplied by RI. AV is RF divided by RI plus 1. AV is 2 RF divided by RI. The correct answer, AV is GM multiplied by RL. In an operational transconductant amplifier, OTA is used as a non-linear mixer, and an audio signal is mixed with an RF signal. The output will be a signal, a square wave, triangular wave, a frequency modulated, FM wave, or amplitude modulated. The correct answer is D. If an operational transconductance amplifier or OTE is used as a nonlinear mixer and an audio signal mixer with an RF signal, the output will be a square wave, triangle wave, frequency modulated FM, or amplitude modulated AM. In this particular case, it's going to be if an operational transconductant amplifier OTA is used as a nonlinear mixer and an audio signal is mixed with an RF signal, the output will be a square wave, triangle wave, frequency modulated FM, or amplitude modulated AM. Correct answer is amplitude modulated AM. When using an OTA in a Smith trigger configuration, the trigger points are controlled by the I out, I bias, B out, both A and B. The correct answer is with I out as well as I bias. So in other words, it's both A and B. An anti-lock amplifier is formed by connecting a PN junction, a diode or a BJT to the input, to the output, feedback loop, inverting and non-inverting inputs. Connect that to an input. To scale down large signal voltages without obscuring lower signal voltages should be used signal compression, logarithmic signal compression, natural logarithmic signal compressions, anti-logarithmic signal compressions. The correct answer is logarithmic signal compressions. A voltage to current converter is used in applications where it's necessary to have an output load current that is controlled by the input voltage, by the input resistance, output resistance, input frequency. The correct answer is the input voltage. The output of a peak detector is always 70.7% of the input, equal to the maximum value of a peak level received since the last reset pulse, equal to the minimum value of a peak level received since the last reset pulse, none of above. And as you can see, the correct answer is B, equal to the maximum value of a peak level received since the last reset pulses. Which of the following correctly describe the relationship between bandwidth and gain for instrumentation amplifier? Instrumentation amplifier have no bandwidth since they can only amplify DC. A bandwidth and gain are both zero. Bandwidth increases as gain increases. Bandwidth decrease as gain decrease. The correct answer is the bandwidth decrease as gain increase. That's number D. Insulation amplifier can accomplish isolations using a transformer coupling, optical coupling, capacitive coupling, all of the above. The correct answer is all of the above. The voltage gain of the input state of insulation amplifier is 12. If the output state has a gain of 6, the total voltage gain is equal to 6, 18, 72, 144. What we're going to do, we use the formula AV total is AV1 multiplied by AV2, and that is 12 multiplied by 6, and that gives you 72. So the correct answer is equal to C, 72. The total voltage gain of insulation amplifier is 49. If the voltage gain of the input and output states are equal, the voltage gain for each stage is equal to 4.9, 7, 24.5, or D, 98. Use the formula AV total, AV1 multiplied by AV2. So AV1 is equal to AV2, therefore 49 is 7 times 7. The correct answer is B. Logarithmic amplifier are used to compress an analog signal, linearize the exponential output from a transducer, perform an anti-lock multiplication and division, all of the above. The correct answer is all of the above. Number 45. What is the required value of a feedback resistance needed in current to voltage converter where each 100 microamp of input current needs to result in an output of 1 volt? A 1K, 10K, 1 mega ohm, 10 mega ohm. V out is I in multiplied by RF. So RF is equal to V out over I in. So RF is equal to 1 divided by 100 microamps. And that gives you RF is equal to 10K. So the correct answer is B. The current applied to current to voltage converter circuit changes from 4 milliamp to 20 milliamp. If RF is 6 to 5 ohm, what is the change in the output voltage? 1 volts, 5 volts, 10 volts, 20 volts. Use the formula V out is I in multiplied by RF. Difference in currents is 20 minus 4, it gives you 16 milliamps. So 60 milliamp multiplied by 6 to 5 ohm gives you 10 volts. So the correct answer is C.